You ever wonder how this works?
It starts here about an hour down Jones Road from University Park at the NRG Texas Power Station. Here, engineers and technicians turn coal into heat, put that heat in the water to turn into steam. That steam is then used to do mechanical work by spinning a turbine, and that spinning turbine moves a permanent magnet at 60 times a second, generating an AC electric current by inducing a current through copper wires. Of course, that was a gross oversimplification, but for the sake of brevity, this is about how we get electricity. We take a heat source, we use it to boil water, we use that boiled water to then turn a turbine, and that moving turbine creates electricity. But I do think it's worth it to stop for a second and examine that last part of the energy chain. How exactly do we turn mechanical work into electrical energy?
This right here is an electric generator that spins a permanent magnet at 60 times a second to generate a magnetic flux. This then induces a current in all three of these wire setups, generating power voltage current through these wires that we can see over here. Now, why do we generate three of them instead of just one? Well, because if we look at just one of these voltage graphs, it goes up and down, right? And for a lot of heavy machinery, this could be an actual problem. We don't want our voltage to have this much variation. However, if we stack three of these voltages together, then we get an almost steady supply of current, which makes it easier to run a lot of heavy machinery without having to convert it into DC and lose energy in the process. The other reason we do this is that a lot of things don't need that much power. And like, even though we're Americans, we use a lot of electricity in our house, we don't need all three of these phases. So we can just take one of these off the power grid because they all travel in separate lines as they move across the country. We send it to a house and the house uses that instead of passing the full output of the generator through someone's breaker box.
Okay, so we know how we make power at this location, but how exactly do we get it to my house? And more importantly, how do we get it to my house without losing all of that power to heat over the transmission lines? The answer is transformers. You see, we use transformers to step up the voltage into these high voltage transmission lines to about between 100,000 to 700,000 volts. And we do this because in the equation for power loss over a line, it's resistance of the line times the current that you're passing over it. So if we try to turn as much of our power into voltage as possible and step down our current to as low as possible, then we minimize power loss, letting us get these voltage lines from here to about where they're going to like 99% efficiency. But once we pass it over these lines, where exactly does it go? I'm here at a power substation, which has two primary roles on our power grid. The first is much the same as the banks of transformers we saw at the power station. That instead of stepping up the voltage, takes voltage from these high voltage lines and steps it down in order of magnitude to between 10 and 20,000 volts. The second role it has, which is equally as important, is regulating the grid. Grid regulation happens in two ways. The first is simply accounting for human behavior. You see, we don't use power uniformly throughout the day. We have a base load, which is the amount of energy that's always needed to keep our society going. And then we have a peak load as people do different things and need electricity throughout the day. This usually happens in the morning as people make breakfast, and at night as people watch TV, make dinner, etc. In fact, in the UK, the power grid has to account for a massive spike in energy demand at exactly 5 o'clock every single day, because that's the time most of the country makes the evening cup of tea. The second kind of regulation our substation does is called controlling power factor. Simply put, power factor is the amount of energy being transmitted over the grid that's actually able to do work. When you connect an inductive load to the grid, such as a transformer or an electric motor, this causes a lagging power factor. This is because these electrical instruments store energy in a magnetic field, which opposes a change to current. This means that the current's change is slightly delayed relative to the sine wave, causing the two waves to be out of sync. Not sine wave, the voltage wave, causing the two waves to be out of sync. This means when you multiply the two together, you sometimes get an output of negative power, meaning you're moving power over these lines that isn't actually available to do work. The same thing happens when you connect capacitive loads, but in the opposite direction, meaning you have your current wave is front shifted. Since these two are opposite to each other, you can use the two to counteract each other and try to get your power factor closer to one, which is exactly what grid operators do. Behind me, you can see rows upon rows of shunt capacitors, which are used by grid operators to regulate the grid and try to keep the power factor as close to one as possible. So why do you want to regulate power factor? Well, for the obvious economic reason, if you're transmitting energy across your grid that's not available to do work, then that's less energy you can sell to customers and you make less money. So power plants want a low power factor. But more critically, if you have a high power factor, then there's less available space on your lines to transmit energy that does actual work. The businesses that pay you to power them are still expecting useful energy. So then they're still going to be calling on current from the grid that doesn't exist anymore because space has been taken up by this useless power. This then taxes the system. Once it reaches some critical overload points, all the generators across the grid, which are synced up, will begin to spin out of control as they can't match each other's turn rates. Once one plant gets to the point where this out of control spin gets detected by breakers, the breaker's going to fall at that power plant. Once that happens, the whole power plant is taken off the grid, and there's even less energy available to do work. Then the other power plants are even more taxed, and they're going to get more out of control. This has a cascading effect until you get a total system blackout. This is exactly what happened in the 2021 winter storm in Texas. However, assuming that everything is working, power will flow from the substation and eventually reach here, my house's breaker box. This pulls power from one of the transformers we talked about earlier in the video and receives two 120 volt lines and one 240 volt line. The 240 volts is used to power high demand electronics, such as my house's drying machine or my oven. Then the 120 volt lines are routed throughout the house, and this is what powers everything else. So this is what comes out of your wall outlet, this is what powers the lights, stuff like that. And eventually, off one of those 120 volt lines, we reach here, my desk lamp. However, that was a remarkably complicated process and really just skimmed the surface of what's going on. So the question deserves to be asked, why do we still use alternating current? Of course, back in the 1800s when we first built the power grid, it was the only option that made sense because there's no way to step up DC to high voltage. Ergo, there's no way to transmit DC over long distances. However, in 2025, we most certainly know how to do this with DC. In fact, we know how to do a lot of the things that used to be AC exclusive using direct current. And DC is an order of magnitude more efficient. It doesn't lead to the catastrophic grid collapses that AC is prone to. So why are we still using it? And for one, we do use it in some cases where it makes sense. For example, there's a high voltage DC intertie between Oregon and LA, letting a city whose power demand peaks during the summer months connect itself to a state with massive amounts of hydropower whose peak demand for energy comes in the winter, allowing both to balance the grid without needing to build power plants that are only on for 4 months out of the year. But for the rest of us, power moves on AC lines because we are using the infrastructure built by men of a different time. We haven't updated our grid in over 60 years, and it really doesn't look like we're going to do that anytime soon. So, for better or worse, all those years ago, when we were first building the largest machines our people have ever known, two roads diverged in Yarrow Wood. And knowing we could not travel both and be one traveler, long we stood and looked down one as far we could to where it bent in the undergrowth. Then took the other just as fair, and perhaps having the better claim, for it was grassy and wanted wear, though then again our passing there had warned them really about the same. So here we tread on leaves no step had trodden black, and oh, we save the other for another day, but knowing how way leads on to way, I doubted if we should ever come back. So I shall be telling the story ages and ages hence. Two roads diverged in Yarrow Wood, and we took the one less traveled by, and that made all the difference. Thank you.